Okay, so we got a lot to cover. You know, one of the biggest complaints I get is we don't spend enough time on circuits, so this is our last day. You can probably understand why, that without doing some of the earlier quantum presentations, this material would not make sense. So we're kind of bootstrapped to go in sequence here. But given that, we'll cover as much as we can with the remaining time that we have, and try to finish up in an orderly way here. Okay, so let's review briefly what we did last time. I'm going to avoid the slides until the very end because it's not as good, I think, for the contrast. It's harder to get everything videoed well. And I think I can explain some things without the slides until the end. So the last lecture we left off was we finished off talking about the IV, which we call current, IV, which is, you know, current voltage characteristics of voltage curve for a PN diode. So we have the diode, and the PN diode is one in which there is positive carriers on doped onto a semiconductor, and the other side has negative implants where some of the silicon curve for PN silicon-based silicon type or silicon-based semiconductor, right? And yeah, so we basically were looking at the characteristics of what happens when you apply a bias voltage across here, and what we found or discussed, or what was we found empirically with some theoretical guidance, was that the curve for this for positive voltage. So by positive voltage, I mean that the positive side is of the battery is connected to the positive carrier semiconductor, and that characteristic curve looks something like this, with the voltage remains 0 until you get to about roughly 0.6, and somewhere between 0.6 and we'll say 0.7, the voltage really takes off. It's very nonlinear, and we'll label this as the voltage axis in volts, and this of course will be the current I or the current. So this is called an IV current. Furthermore, we said that if we do the reverse biasing of the diode, namely that we change the orientation here so that this becomes the negative side and this becomes the positive side, that the diode will not conduct current. There is no current flow until you get to a breakdown voltage, which this is a nonlinear scale at minus 12 volts, and then the current zooms off, and the voltage is bounded below by 12 volts, which is called the breakdown voltage, and it's bounded above by around 0.7, where the current becomes extremely large, jumps way up. Okay, so that's what we had last time. It was the IV characteristics curve for a junction diode, a PN junction diode. And now we're going to want to do is talk about some of the applications for the diode. So one of the first ones that is mentioned in the book or in your chapter reading is the use of diodes for rectifiers, and so we call, or what we call, another bit. What we call voltage rectifiers. And the idea of a voltage rectifier is that what we can do is we can, if I replace, let's make a new circuit now. Do you want me to erase this or redraw it? You don't care, right? Works either way? Okay. So let me just modify this one. For those of you, if you want to take notes, you just draw a new picture. It's not that much different. But let's say, for example, that that what I want to do is to what we would say rectify or connect this diode to an AC power source, and this would be, you know, some voltage. We'll say V0 times sine omega t. So sine omega t is the voltage as a function of time. It swings positive and negative, and I can hold either side to call my to ground or ground potential. So I'll put the ground side over on over on this one. Okay. Okay. So now what I have is I'm going to take a particular example. Let's say that we want V0 to be around 11 volts. And of course, the reason why I'm taking it this way is because I want to avoid the negative, the breakdown voltage. This is called the breakdown voltage on the negative side of the IV curve. Okay. So this thing is going to swing between plus or minus 11 volts on the output side right here. So this would be the output side where the voltage is swinging between plus or minus 11 volts. Okay. So what happens here when I connect this circuit across a resistor? Well, we know that this thing is only going to conduct when I get above 0.6 volts. Now, sometimes the examples use 0.6 as the threshold, and sometimes they use 0.7. I'm going to use 0.6 here in this example, and say that this is the threshold. But once if it really turns on, it will go up to 0.7 volts, right? And that's where the diode is what we would call full on, or when you're trying to drive it much as high as possible. So this particular this circuit is going to have a current generated through here, and just as we did last time, we will expect that there will be when this side is positive. Right? So let's draw the current source. I'm sorry, the voltage source. So the voltage source will have a sinusoid that looks something like this, right? And I'm trying to raise this up. This will be my source. So this will be V source. And now I want to measure on the output side the voltage across the resistor, so VAB, right? So this will be my output voltage. Well, okay, so what am I going to see here? Well, what's going to happen is that until I get to 0.7 volts on the positive side, this thing is not going to conduct, or let's say 0.6. Then, so what that means is that in the very early part of the positive going voltage, the voltage out, or what I call VAB, is going to remain 0. Now remember, this is a time plot, and we'll draw a time this way. And so far, that's all I'm not going to mention what the frequency is. So now what happens is I go above 0.7, and the diode begins to conduct. So it rises up and it goes up, and it follows the voltage curve, except that if this is, for example, 11 volts, then the voltage across the resistor is going to be 10.3 volts. Right? So in other words, it's going to be 0.3 volts lower because there is the voltage drop across the PN junction or diode is equal to 0.7 volts when it's conducting. So I now have a situation where that voltage is going to go up to this amount, and then it's going to come back down, but as soon as it gets down to 0.7 volts on the downside, it stops conducting. So it does this. Okay? And similarly, as it goes negative, well, this is reverse bias, right? The diode doesn't conduct in reverse bias mode, so the voltage stays flat until it goes positive again. So the voltage stays flat out to here, and this will be the zero crossing. This will be 0.7. It goes to 0.7, and then it will rise up, and it will repeat again, except that the voltage level here will be 7/10 lower than the source voltage because of the drop across the diode. Okay? So this gives us a general picture of something that is this particular type of voltage display is called a half-wave rectifier. Half-wave rectifier because it rectifier because it maintains the positive part of the voltage cycle, but it takes out the negative. So I've basically now converted a bipolar voltage source to a single-sided voltage source. So the voltage is always positive across this resistor VAB. So this is VAB, this is VAB, and this is what I get. Okay? So the diode rectifies the voltage so that it's only going to allow current to flow in one direction, which is this way. Current cannot flow the other way, which would be reverse bias. Okay? And furthermore, since the negative side never gets below 11 volts, then you block the voltage or the current, the zero current flow through the diode, and therefore there is zero current flow through the resistor. So if there's zero current flow through the diode, there's zero current flow through the resistor. Okay. Any questions on this so far? Yes?
Is VAB like this current through the resistor?
Say it again?
VAB, is that just current through the resistor?
No, VAB is voltage. So this is VAB. It is the voltage between point A and B, which we just refer to opposite sides of the resistor. So there are points on the circuit. Okay? There are points on the circuit. Okay. Did that answer your question? Did it answer your question? Now, it's easy to get current because we did this problem last time that I can get the current through the resistor, I through the current I. Obviously, this is a closed loop, right? So whatever current there is through here is the same as the current through the resistor, and vice versa. But the point is that this is just equal to voltage divided by R. So this would be equal to 10.3 volts divided by the resistance, right? So divided by R. I put in your favorite value. And the point is now that it's still going to be the same. It's going to follow. It's clearly they're proportional, right? If voltage changes as a function of time, then this would be I max, by the way. So let's put this. Let's call this I max. So I max is equal to 10.3 volts divided by R, because this is equal to V max across the resistor. Right? And so if I were to do therefore they're proportional, right? This curve in voltage is going to be proportional to the current that is flowing across the through the resistor. So I can also do it, right, it will look exactly like the voltage plot, VAB, only I just divide it by R. So this should, by the way, VAB, I forgot to put that, VAB divided by R. And so it's going to have the same form. Right? It's going to go like this, and it's going to go like this, and etc. Right? So now this peak value is equal to 10.3 divided by R, right? right? That's the peak, but this becomes current versus time. Right? Did I make that clear on these plots? These are time. These are time plots. Okay. Any questions on it? It's pretty simple, right? Pretty simple. Yeah. Okay. Good. Okay. What next? So that's a half-wave rectifier. Now, something that's more useful is something that's called a full-wave rectifier. And I wonder if it's useful to erase this board. Do you think this needs erasing for the video? No. So another more useful one is what's called the full-wave rectifier. And it works something like this. And the reason why, by the way, we're going to actually look at a specific application. Not only are we going to talk about full-wave rectifier, but we are going to talk about a transformer. This is an application of a transformer from 120 volts AC to 12 volts DC. Only in my example, I'm going to use 11 volts, and it's just because it's easier to describe this way with the conditions of the diodes that we've already set. But you can make it 12 volts. And obviously, the most important reason why this is important is because all of our charging devices for our phones and computers and cameras, charging devices, use a wall current of 120 volts, which has to be converted to 11 or 12 volts DC in order to charge our device. Now I stayed at 11 just because our previous example shows breakdown at 12, so we start a little bit short of that when we talk about the AC, this properties of this. So the basic idea is that we first of all we take the wall power and we go through a transformer which transforms the high voltage AC power. So this is what we will call AC. Now, one thing that, if you don't already know that, 120 volts is not the peak voltage out of the wall. Does anyone know what the peak voltage out of the wall is? Yeah.
240. If it's multiple phase, 240.
Well, you can make 240, but they refer only to the RMS. In other words, of the sine wave. So, in other words, the root mean square. It's sort of like the average value. If I flip this over, if I squared this function and took the average value, I would get 120. So the peak value, even for 120 volts, is really 170 volts. So this is actually 170 volts times sine of omega t. Right? We call it 120 volts, but it's not really 120 out of the wall. Okay, so that's one thing. Then the other point is that we have to transform it down, so we've got to go through another winding of coils, and usually this is done, in an iron block, right, or some magnetic material like iron or something like paper, so that we can use the mutual inductance. And I probably should draw this a little more. Maybe I'll try to draw this a little more accurately. That we have the inductance loop that would actually go something like this. That look more like an inductor, and so the magnetic flux can go through here, and we now we use some relation from our earlier two electricity and magnetism, which says that the voltage, if this is the primary voltage V1, then the secondary voltage V2 is equal to, there are N1 windings on this loop, and there are N2 windings on this loop, and so V2 is is N2 divided by N1 times V1, right? So if I make this approximately 1/15 times 170, then I should get a V2, which is a little bit less than 12. Including before class, I'm going to call it 11.7 volts, something like that. Okay. All right. Okay. So that's just simply using transformer theory, right? We step down the wall voltage from 170 down to 12, or 11 and a half, whatever. And now what we have to do is convert it to DC, right? So the way we convert this to DC is, I'm going to rewrite this now because this is getting a little bit messy. And I'm just going to redo this part of the secondary winding because we've already stepped down the voltage. So we'll just look at this as being driven by the transformer in the wall. But I'm going to rewrite the coil this way. And what I'm going to do is I'm going to put in a diode on both sides of the transformer. One on this side and one on the other side, both conducting in the same direction. So remember, every time you write a diode symbol like this, then what you're really doing is you are writing this as a P and an N, right? Which means that under positive potential applied from left to right, that it conducts in this direction, right? This conducts in this direction. Okay. You know, when the voltage across PN is greater than 0.6 volts, right? That's when it conducts. So unless you go above 12 volts, it's not going to conduct the other way. So we just leave it as looking at, we're only using it in the forward bias or the forward bias direction of generating current. Okay. So now what we do is we take the outputs across here, we connect them together, we draw a resistor through here, and we define this point as our ground potential. Right? Remember, in a circuit, I can connect any point I want to ground. In your car batteries, your negative terminal is called the ground. I could make a car battery circuit and make the positive side ground, and then the negative side would be at minus 12 volts, right? So I have the flexibility in a circuit to define where I want the zero potential to be. I can choose what point in the circuit I'm going to ground or call zero. And ground is that infinite reservoir of conducting electrons that's, you know, connected to the metal and the table and the floor. And if I have a large copper piece of stranded wire and I nail it to the metal in the floor, that's my infinite ground, right? My infinite ground. By infinite means infinite reservoir. I can pull as much charge off it as I want. It's not going to change the charge of the ground significantly. Okay, so that's just a backdrop on grounds, in case you wanted to know a little bit more about that. Now, what is happening here when I ground the middle point is that in half of the cycle, this side goes positive and this side goes negative. But in the other half of the cycle, if I wait, and by the way, now we will point out that it is important to specify that omega is equal to 2 pi times the frequency, which is 60 hertz, right? So the wall power is 60 hertz, and so this oscillation from the source that we are now considering is going to be 1/60th of a second, which is 0.016 seconds is the period of the 120 hertz from the wall. And that voltage oscillation is preserved when I go through the transformer. It still stays there. But a half a second, so in another half a second, if I look at it a half a cycle later, then what happens is that the plus and minus sides have reversed on the diode, and now this side is negative and this side is positive. Okay? So this is 1/2 cycle later. Right? And 1/2 cycle later, then, boom, I got the resistor here, and this is connected to ground. Okay? So what happens now? In the positive half of the cycle, when the AC voltage has gone positive on this side and negative on the other, with respect to ground, then this diode becomes conducting when this positive side gets above, when this positive voltage, which I will try to call let's see if I can do this in a way that's consistent. So I'm going to call this point C, and I'm going to call this point D. So, and of course, this point will be ground, which we'll just call point O. But when this potential V, we'll say V plus, gets above 0.6 volts, then this one conducts, right? But at the same time, this one is below negative 0.6, or below 0, as a matter of fact. So there is no conduction, no current through this leg. No current here. Okay? But there is current flow through here. So now, if I take my 11.7 volts coming off the top, so let's say I'm at a maximum excursion of 11.7 volts here, it drops 0.7 volts, now 11 volts on this side, see? And it goes through a resistance R to ground, right? So I can calculate then that my voltage, which I'm going to call VAB, right? AB is the voltage across the resistor, as it is over here, VAB, that voltage is going to be equal to, so VAB max is the VAB max is 11 volts. Okay, so this is equal to 11. The current max is going to be equal to 11 volts divided by R, right? If I take, I'm sorry, did I say it right? Yes, I did say it right, correct? Yes, the drop is 11. So I get a maximum current of that amount. Okay, so that's what happens in this leg. This one does not conduct, this one does, because this side has gone positive in the AC transformer. So when this side is at positive volts, this side is at negative. And then a half a cycle later, they switch, and this side becomes the negative side of the transformer, and this one becomes the positive side. So now this one does not conduct current, does not conduct, right? Because the polarity of the voltage through the diode is negative, and therefore there's no conduction. And now what happens is but this one now is positive, so it does conduct. So the current now goes this way. Okay. So what happens is that regardless of whether the phase of the sine wave is positive or negative, I will still get the same direction of current through the resistor, and therefore the potential drop across here is always greater than 0. All right? Potential drop is always greater than 0. So furthermore then, what I can do is say that if I were to draw this rectifier out, that the response, so this is VAB, right? In the first, from 0 to 0.7, there's no current coming out at all. Well, so it stays relatively flat. Then it comes up, it goes up to its peak value. It comes back down when it drops to below 0.7 on the sine wave. So maybe I need to put another sine wave up here, because the idea is that there's a reference going on here, right? So if I were to draw these in time, so this is in time for the two plots, and this is the V from the source. And the source is oscillating up and down between plus 11.7 volts. And I'm going to make this one go to minus 11.7 volts. and therefore the voltage across the resistor is been reduced down to 11, because it gets 11 volts, because, there's a 0.7 volt drop in getting across the diode. There's a 0.7 volt drop in the, going across the diode. So it's not going to go far as high across the resistor. Let me take this out, give me a little more space to write. This axis is VAB. This volt is 11 volts, and this is time. So now what happens is that we get, regardless of what part of the cycle it's in, except I didn't line them up correctly, so let me go back and try to fill this in a little bit better. So this point right here lines up with this point right here. This point right here lines up with this point right here. This point right here lines up with this point right here. Okay, so now I've got everything sort of lined up. So what I see now is it goes up, back down, goes back up. It's a little bit hard to see from this angle, but I'm try to do it anyway. So now this thing goes up, and it comes back down, and then it's flat, and then it comes back up, goes back down, it's flat, etc. Okay? That is full wave rectification. Full wave rectifier. Okay? Now, still not quite finished yet, because what we really want to do is to make this a DC. So what we really want is to be able to use this for a charging device, is that we want the voltage as a VAB as a function of time to be at a constant value. We'll call it 11 volts. Now, like I said, we can always make a new transistor, new diode that breaks down at a slightly higher voltage, but for this example, I wanted to keep the numbers as closely to the same as our previous lecture, and also the discussion in the book as possible. And so this is what we want, right? We want this, and so far we get this. Okay? So how do we transform this sine wave into this constant voltage? Well, the answer is that we apply a standard circuits trick that basically says that if I put a capacitor in parallel with this resistor, it will smooth out the ripple. And we're not going to go through the derivation on this. There was some practice problems in 273 that you should have worked with. This is called an RC circuit. And the RC circuit has a time constant. And the time constant, or tau, which is what we'll call it the relaxation time. The relaxation of voltage back to zero. To zero is given by the product of R times C, which is in units of seconds. Right? In case you didn't know, if you multiply resistance times capacitance, you get time. Right? So what it also tells us is that relaxation can be described by e to the minus t divided by RC, where RC is the time constant. And so if I have a voltage that starts off at V0, it's going to fall back off in a time constant equal to RC on the time axis. So if I start the voltage at V0 and I now disconnect the voltage, how long does it take for that voltage to bleed off of the capacitor? That's called the RC time constant. Anybody seen this before? Yeah. Okay. Good. Right. Called the RC time constant. So what I do now is I want to make RC. I want R to make RC much greater than the cycle time, than the time between these cycles. So I want them to be, or in this case, half cycles. So you'll notice that this is one full cycle, which is 0.016 0.016 seconds. And so this is 0.008 seconds, right? That would be half the time. So a half cycle of 60 hertz is 8 milliseconds. It's a half cycle of 60 hertz. So now, if I want to make this RC much larger than 0.008 seconds, then what happens is that even though the voltage has been turned off, or disconnected has been turned off, it begins to fall back down with a very long time constant, right? And then before it can get to 0, the next part of the sine wave comes back up again and boosts it back up. And then it begins to bleed off and fall back down because the capacitor is losing its charge, but then the next pulse of voltage comes up and bumps it up. So the end result is that I get a nice smooth voltage that is much more regulated than I had with the pure rectified sine waves. Okay? And that's how you do it. Now, typically speaking, for electronic devices, we want that the delta V, so if I define delta V as the ripple, so let's call this the ripple, right? That would be the peak-to-peak difference. So let's call the ripple this difference between the max and the min, right? That's delta V. Right? This delta V ripple should have the property that delta V divided by the average voltage, which in this case is 11, should be less than or equal to about 2%. Right? So even though it's never going to be exactly completely smooth, it will be approximately smooth. And as long as the voltage is stable to within a couple percent, the electronic device doesn't care and it gets its full charge. Okay? So that's how that works. Any questions on this? While you're thinking about that, I'm going to get the other slide put up for the rest of the lecture. So that's the there's some things we don't have time to go into. You need to read in the book how you can use these diodes can also be used. This principle of the diode of the conduction of negative charge carrier electrons over to the holes involves the change in the energy levels. We showed the energy level diagram. It is responsible for how LEDs are made, light emitting diodes. They can be used for photodiode is a way to detect external photon light. So I'm going to rely on you to read that because otherwise we're not going to get done. And I'm purposely covering the more difficult parts so that leave the easier parts for you to do your own reading on. We can't cover every aspect, unfortunately. Any questions?
Are we going to take the conduction angle into account?
What do you mean the conduction angle?
Or I mean because you're actually not, the period is not fully 0.008 because of the,
because of the fact that it gets to 0 before that.
Yeah.
Yes. Well, yes, you're right. You're right. So there's a what you might call an angle or a time period in here where it's 0. But this distance is small compared to this distance. In other words, this contributes most of the time. This is a very small part of the time. But the midpoint between here is 0.008. The midpoint in the 0 region here is 0.016, etc. The point is that if you make RC much larger than 0.08 seconds, it really doesn't matter because it is you're trying to prevent this droop, right? And the worst case scenario would be if I drop the voltage immediately to 0. It would still bleed with this time constant. But you're actually holding the voltage up. So I don't know a better way to describe it. It's just that this is, as long as you satisfy this condition, then you can make that ripple less than 2%.
You're just using the 2% as the parameter,
As a parameter for, and what I believe, you have to check me on this, what I believe that the electronics industry would consider a minimum requirement. You can probably do your own research on Wikipedia and maybe get better feel. But if I recall, that's sort of the ballpark number that you're shooting for. Okay? So up till now, what we've talked about is the junction, making a junction diode. So we take a P-type semiconductor, attach it to an N-type semiconductor, and form the diode. And this diode builds up a potential difference, and it has this IV characteristic. Now, let me go back a second. There is another type of unit, which also got the Nobel Prize for, the transistor, discovered or began to use massively in the 1950s, 1960s, that replaced the old vacuum tube designs, which were very large and bulky and expensive and filled with glass tubes that performed the same function. This was the beginning of the miniaturization of electronics. And the basic idea of the transistor is that we sandwich together three semiconductors. One has a very thin region in the middle with two thicker ones on the end. And so instead of producing a PN junction, we can either produce an NPN junction or a PNP junction. Okay? We can do either one. They can be both types of transistors can be used. We're going to talk about the NPN for our example, just because it's easier if we focus on one particular application and not try to generalize too much as we go through this. So this is exactly what they are. Now there's names given to these three locations on the triode, right? If two of them makes a diode, then three of them makes a triode, and the triode is a transistor. There are three joint connections to the three materials called the collector, base, and emitter. Okay? These are the three connection points to the transistor, and they are drawn schematically in diagram form like this, with a big circle around, an arrow going out, which is the direction of current. So the names, let's see if I can, the conventional current flow will be from the, let's say, the positive conventional current goes from the positive hole carriers to the negative. Electrons go in the opposite direction. So looking at this as an emitter, I'd be looking at conventional current being drawn into the lower part of this PNP junction. So there's where the emitter is. The collector actually collects electrons, right? The electron. So in the normal operation that we were going to discover is that when this device is active, we're going to get a large current, not only going through the P through the N, which is forward bias here, but also from NP to N, down all the way through here. So the general flow of current is going to be vertically down, either from the base to the emitter or from the collector to the emitter. Now, it does appear that if I have a positive bias between the positive and the between the positive emitter and the negative, the positive hole carrier and the negative or the N-type semiconductor with the electron as the carrier, that the conventional flow of current will in fact be in the vertical down direction, which is what I just mentioned to you. It turns out that oftentimes, even though this potential up here is higher than the potential at the positive pole carrier, if this region right here is thin enough, and if this voltage between PN is large enough in the forward bias case with positive voltage on the P side and negative voltage on the N side, that the conduction from the top will also be very large. But it does depend on the fact that this is a very, very thin layer, typically less than a few microns in thickness. So it's a very, very thin intermediate P layer sandwiched between two N-type carriers. Okay? Questions? Yes?
So I have a question. So the term, so would NPN be a source then?
No, NPN is a type of transistor. NPN is the transistor on the left, PNP
Okay.
is the transistor on the other side. Yeah, that's a good point. It's not clear from you. Any other questions? So the transistors are referred to as NPN or PNP, just like the diode transistor is referred to as a PN. Okay, so we're going to look at example of here. Then I want you to etch this circuit into your brain, into your memory, because it's important for homework problems and also for understanding one of the homework problems anyway, but also for understanding how this whole system works. So the way we approach this, and I guess maybe the first thing is to tell you the end result of how to look at this picture globally before we get into the details of what's going on, is to think of it that there are a number of components on this circuit that we should go through. First of all, there is a voltage, which we call EC, which is the collector voltage, which is keeping this collector up at some positive potential, usually 2 or 3 volts above ground. For simplicity, we are going to, remember we said we're at freedom to choose any point to be ground in the circuit. That's our 0 voltage reference, right? I'm going to choose this line of the conductor right here to be my zero voltage point, right? Everything relative to here is zero volts, right? Everybody got that? I'm going to tie this line right here on the circuit to ground. Okay, so going on the right side, I have a voltage source through a resistor, through the transistor, and in principle, I can get some current loop flowing through this leg right here if I've got the right bias on this triode or transistor. On the other side, I have a second power source, which is connected through a resistor which is connected from the resistor through the transistor or triode back down to ground, and this forms a closed loop. So in general, there are going to be 2 closed loops of current in this circuit. One of them is going to circulate counterclockwise around the second leg, which also flows through this output resistor. And then there is a current that's flowing clockwise through this leg right here. Okay? And we're going to assume for right now this input signal is 0. So the reason we're doing that is that we're going to add the signal later, right? So we have two steps in this process. One of them is called the quiescent state. Quiescent state. Okay. It means that there is no external signal provided. And by signal, by the way, I am generally using the concept of an amplifier. And what this is actually what we're talking about here. We're going to describe this device as an amplifier. So what we want to do is to no external input signal. We want to take an external input signal and amplify it to a large output signal, right? So we want input and voltage or current amplified to a larger I or voltage at output. Right? That's what an amplifier does. Right? It takes a small level signal and amplifies it into a big level signal. So that's the path we want to get to. Right? That's the goal of the discussion. Is how do we show that this circuit is doing exactly what I've just written down. Okay. So this is the scenario that we have. Well, first of all, we're in the quiescent state. In the quiescent state, no external input signal. There will be a base current. There will be a base current, and we'll discuss this in a second. There will be a base current, and there will be a collector current. So remember, one loop of current in the base is the closed loop on the left. There will be a base current, and the closed loop on the right is called the is where the collector current flows. Right? So we have a base current and a collector current, two loops of current. All right. Now, the way we are going to start this initially is that and I'm going to redraw the triode in a little more detail here. Is that we are looking at NPN junction. We are looking at the base voltage. Well, there's going to be what we call the base voltage here. Let me just redraw this circuit. And there is going to be like that, okay? So what we are going to establish, and we said, of course, that this side we're going to put at ground, so this is 0 volts down here, and of course this goes to the other leg of the circuit, which is going up through the output resistor, and I think let me see, yeah, the output resistor, and back to the top of the triode. Now, you remember that in a PN junction, that the characteristic is that if the voltage is forward biased across the PN junction so that I get to at least 0.6 volts, then I've got some conduction, and by the time I get to something close to 0.7, I've got a huge amount of current flow, right? So here's what we're going to do. This is going to be, we call this V base to emitter. So this is VBE. Right? This is base to emitter. We expect this sort of I'm sorry, this should be correct. I labeled the axis wrong. This is VBE, and this is the current through the PN junction. Right? We expect this to happen. And so what we are going to do in quiescence, in the quiescent mode, we are going to be operating right here. So in quiescent mode, we'll get the transistor is, I'm sorry, this part of the transistor, the diode portion has some conduction through here, and we get some circulation of charge. Okay. Now, that is one of the most important key points. So now what I can do is say that this VB, I can write an equation for VBE. VBE is equal to, using the circuit law, this is equal to the voltage labeled E sub B in the figure, I believe, E sub epsilon sub B, is equal to epsilon sub b minus the IR drop across the base resistor. So we'll call this IB times RB. Okay? All right, and in quiescence, this is 0.6 volts. This is in quiescence. That means no external signal, right? It's just sitting there waiting for a signal to be amplified. So we are sitting right here. Let me add a little more light while I can. I think you don't need to look at that. Let's see if I can. Yeah. So this will probably show up better on the film too. So we're quiescently operating at this point right here. All right. This is where we are operating while we're waiting for a signal. And this thing is sitting right where there's with slight conduction enough to get current flow through the lower part of the transistor. Now what I'm going to do is I'm going to put a signal over on this side. And this is going to be what I call the signal source. Now I'm going to say I get a signal source. Now there's a lot of ways we could do. We could be talking about audio signals that we want to amplify. You want to get a louder sound, or you more intensity out of a light at the street corner. You want to amplify the light output. I'm going to talk about amplifying a radiation detector signal. Right? I'm going to talk about what happens if I have a radiation detector, and my radiation detector can consist of a number of different parts, but the simple one that I'm going to draw is that I want to detect electrons that are passing through my detector. I want to be able to detect electrons. So I get let's see if I can change my color stream here. So I get a track of electron that goes through this detector. And when it does that, what happens traditionally, or maybe most detectors, is it generates a stream of ionized particles in the detector, which, if it's a gas detector, for example, it might be ionized air, it might be ionized argon, it might be ionized, some sort of gas that gets ionized, right? So it's an ionization. So as a result, I now apply a voltage between the what we call the cathode and the anode. So this outer can voltage will be at a positive, I'm sorry, at negative potential with respect to the center right here. And I'll put a high voltage so that I can collect the electrons onto the wire. Right? So the electrons are collected onto the wire. And this wire comes out and has the signal that brings in the electron signal to my amplifier that I want to amplify, right? So what happens when a signal comes in? Well, electrons are going to flow out to reach their to reach their lowest potential, but if I have it designed so that electrons are flowing out, then by conventional current, what happens is that the conventional current is flowing in the opposite direction, right? So the signal generates a smaller value of current, which I'm going to call I sub B. Okay? Now, what that means is that some of the current is being drawn away from this base resistor. This is, of course, the base resistor. And what's going to happen is that if I draw some of this current IB away, then the voltage at the base is going to increase because there's less current through the resistor. So I get that this is equal to minus IB RB plus minus I signal times RB. So in other words, the see if I can find a better way to express that. It is the, this should be plus, so this should be minus. So this is EBE, this is the source, EBE, minus the base current times the resistor current times the base resistor, I'm sorry, minus the signal, where in this case I'm calling the IS the source current equal to, the source current is equal to the, is equal to little IB, which is the extra current going through the base. The extra current through the base resistor. Sorry, the pens are getting bad again. No. So, where does that leave us? Okay. So, the upshot of all this is that the volt VBE is increased. And it only has to be increased by a small amount. But in particular, if it's increased by, for example, increased by 0.05 to 0.1 volts, then what happens is the current, the voltage between the base and emitter has gone up by 1/10 of a volt, and now this current begins to rise very, very dramatically. Okay? When that happens now, by making a very small change in the current through the base resistor, I get a very large increase in the current through the PN junction. Right? And furthermore, because this is sitting at even higher potential, for example, of around plus 5 volts, compared to this, which is sitting at around 0.6 to 0.7 volts positive, then when this begins to conduct, this one also begins to conduct, because this region is so thin that the current can now simply propagate straight through the junction of the negative carrier and the positive carrier. The result of this is that the control of the current, so is that the voltage VBE acts as a floodgate. And the floodgate is that once this voltage at this point gets to 0.7 or significantly above 0.6, the current begins to rush through here and also open up the channel going across this way as well. This is a very, very small barrier, which is less than 1 micron in thickness, and so the barrier becomes penetrable when the current rushing across here makes the whole thing conducting. So the basic idea, to the best that I can tell you, is that this voltage acts as a floodgate. When VBE increases by 0.1 volts, then the current ICE and IBE increase dramatically. Okay? So the idea is that once this point, I'm going to keep saying it again and again because it's a very, very important point. When this voltage changes from 0.6 to 0.7, the current begins to rush across here and also through this way. In other words, this acts as a gate. It's a floodgate. When it's below 0.6, there's very little current and very little current coming through this link. In fact, in the steady state condition, there will be some current I sub C that is flowing through there. That's what the capital I's are in here. The capital I's are the quiescence. Those are the currents when there is no source present. When you apply a source at little IB, then you get a large current change, IC, coming through there. So the amplification is from a small IB, which is the small signal from the source, gets amplified into a very large current through the collector. Right? Because the voltage between the P and the N, or the base and the emitter, are acting like a floodgate. Right? Now, we don't have time to finish the whole argument, so I'm going to have to take the rest of it up on part of our first 15 minutes on Tuesday, but I think you have enough to read the book and get the idea. And the basic idea or important parameter is there's a gain factor that is associated with the amplifier, and the gain factor, beta, is equal to the ratio of the transient collector current divided by the signal current, which is IB. Right? This is called the gain. And we'll talk more about the application of that gain on Tuesday because we're running out of time. All right.